Now here's a setup for a lab that we're very likely to do. I've got a domino lying on its flat side, and then one lying on its long edge, and then a domino lying on its long edge. I'm going to run a ramp from here to here, and I'm going to move this down here. Okay, so I can put, well, actually I don't have to put a domino down here. I can simply set another ramp here. Now I'm going to have to move things over just a little bit, so I'm going to pause for a second. So now we have two ramps. This one just goes down to the level here of the surface. So the slope of the first ramp is less than that of the second. And if I roll a ball down this ramp from rest, it takes longer than if I roll a ball from here, rolling from rest. So that we can see clearly the velocity here is going to be greater than the velocity here at the end of the ramp. So from that information and the lengths of the ramps, we could, if we timed the ball, let's say we time it with a pendulum, 1, 2, 3, 4, 5, 6, okay. Actually, okay, release 1, 2, 3, 4, 5. Okay, it took about 5 counts to get down this ramp, and let's see, get down this ramp, about release 1, 2. Took a little more than 2, but let's just say it took 2. So we travel down this, and 5 counts, we travel down this in 2 counts. This is 60 centimeters. Let's go, that's full-size centimeters, real centimeters, not full-size centimeters on the copies, but real centimeters. 60 centimeters here, 60 centimeters here. So I'm not going to write this all out, but if you divide 60 centimeters by 5 counts, you get 12 centimeters per count. That would be the average velocity. The final velocity, since we started from rest, and we assume uniform acceleration because it's a straight ramp for reasons that we'll understand later, the final velocity is going to be double that, or 24 centimeters per count. Here, when we released it, we got when the ball was released from here and then went to this ramp, it went down this ramp in 2 counts. So that on this ramp, it had an average velocity of 60 centimeters divided by 2 counts, 30 centimeters per count. Its final velocity would have been 60 centimeters per count. Now what we really want to do is analyze the motion just while it was on this ramp. After rolling down this ramp, it attained, at the end of the ramp, a velocity of 24 centimeters per cycle. On this ramp, it averaged 30 centimeters per cycle. So how fast was it going at the end of this ramp? Well, if it started at 24 and averaged 30, what would you average with 24 in order to get 30? It would have to be 36. 36 is as much bigger than 30 as 30 is than 24. Okay? So you see that we're analyzing the motion on this ramp, but not in a situation where the initial velocity is 0. We used the first ramp to attain some known final velocity, which will become the initial velocity at the instant the ball goes onto the second ramp. And then the ball will travel down the second ramp in some time, and we can use that to find the average velocity, and then we can infer from the initial and average the final velocity, and that would also allow us to infer the acceleration on this ramp. Then we could roll a ball down this ramp by itself, 1001, 1002, okay, 2 seconds, and determine the acceleration on the ramp. And we could time the ball on this ramp after having gone down this ramp, knowing this velocity, the change in velocity would be from 24 to 36 centimeters per second. And we could take that change and divide by the time and see if we get the same acceleration that we obtained when we roll the ball from rest on this ramp. So there's a lot of things we can do with this setup. But anyhow, this is the setup. And my main point for showing you this is simply to show you that we're using the same type of reasoning that we used here to analyze these ramps, and also to tell you that the third problem on this problem set, which is assigned, requires this kind of reasoning, but you don't have an initial velocity of 0. So how do you adapt this reasoning to a situation where you don't know, or where you have an initial velocity which is other than 0? And how does that help us inform what we're going to do when we do this sort of an experiment?